Looking at hash functions, we can start to think about what actions they perform and how fast it can be done. When it comes to inserting something in our memory space, well, it's going to be O of 1. We hash the key, such as grapes, through the hash function and places it automatically into the address space that it comes up with. Lookup is the exact same. We access the property. That property is going to get hashed and direct us exactly to the address to find the values. What about deletes? Same thing. We simply use the key. Right away, we know where to delete the item from. And because it isn't ordered, we don't have to shift indexes like we did with arrays. Everything is just nice and simple. What about searching? If we want to find something in our basket, like apples, well, that's easy too. We simply use hash functions. If we go to our playground, in JavaScript, I can create an object. Let's say let user, and this user will have property of age 54. Let's say that the name is going to be Kylie. Magic, well, let's say Kylie does have magic skills, so we'll set it to true. And for fun, let's say that the scream is a function that will just console.log a scream. That was not the strongest of screams, but I don't want to scare people around me. When I run this, I've created a user object, and the age 54, name Kylie, magic true, scream, and this function are all going to get placed somewhere in memory at different addresses. But I can access this really, really fast. I can say user.age, which is going to give me 54 at 01 time. Perhaps adding a new property, I can just simply say user.spell is going to equal abracadabra. And if I run this, and let's just check out what the user object gives us, we see that we now have the spell abracadabra added. This again is access of O1, is O of 1, because we take it through the hash functions and the computer decides where to put both spell and abracadabra in memory. And if I run user.scream, same thing. Oh, I cannot spell scream. Same thing. I get to access this function in memory really, really fast at O of 1. How amazing is that? And I know what you're thinking. Hash tables are amazing. We should be using them all the time. And you're right, we should be using them in a lot of cases. But as we know, there's always pros and cons. Now, let me talk to you about one of the main problems with hash tables. And I have a nice visual to demonstrate this for you. I'll link to this in this video so you can play around with it later. I have a little animation here where we have 12 memory spaces. Remember, our computer has limited space. And when we create an object or a hash table, the computer decides how much space to allocate. It's not going to allocate all the space to the hash table. It's going to allocate a bit of it. And I'll show you later on when we implement our own hash table how we can adjust the size. But seeing that there's only 12 spaces, you can imagine if I insert here, let's say 1. Let's see if I can make this bigger so you can see it. Yeah, there you go. I'm going to insert, let's say the number 3 gets inserted here. Let's do 55. Insert it. Ooh, what happened there? Did you see that? The hash function randomly assigned a space in memory and put it in 3. Uh-oh. remember, there's nothing telling the hash function to evenly distribute until everything is full. Although hash functions are optimized to try to distribute this data all over, it also matters what we put into it. So when 55 gets hashed, well, this hash function generates the address location of 3 to put it in. And because we already have 3 there, it does something funny here. Let's keep adding here and see what happens. I'll add 2, maybe add 12, and finally add 14. Uh-oh, it did the same thing again. And what we just noticed here is something called collision. And a collision looks something like this. We have the keys. Let's say we're inserting the name and the phone number of a user. And we initially place John Smith. This key gets hashed, gets placed in the address space of 152, and gets stored. Remember how I said it actually stores both keys and values? It stores in something called buckets John Smith with the value, that is its phone number, right here. And then we keep going with Lisa Smith, then Sam Doe, then Sandra. Oh no, as soon as we hash Sandra D, it becomes the same address space as John Smith, and we have a collision. And because of this collision, we need a way to store both users somehow in this address space. And something funky is going on here with this little circle and then a point and Sandra D. And just a hint here, this is actually a new data structure that we're going to learn about called linked lists coming up. You see, with hash tables, we can't avoid these collisions. With enough data, with limited memory, we're always going to have this collision. So there is a possibility, if we go back to our example, and I refresh here to start from scratch, that we constantly just add, despite our hash table that's really, really fast, constantly just keep adding to the same memory space, which slows down our ability to access or insert information. Because now, if I want to check what's in this address space, I have to go 1, 2, 3, 4, 5, and so on and so forth. Theoretically, when you have a collision, it slows down reading and writing with a hash table with O(n) divided by K, where K is the size of your hash table. And remember, because we remove constants and simplify things, it becomes an O(n) operation. Now, collision will likely happen in any hash table implementation. And luckily for you, you're never going to have to really implement it yourself. And it's not a very common interview question, but you do want to know about it so you can talk about it. There's 2 common ways to deal with these collisions. I showed you one of them with something called linked list, which we'll talk about later on. But if we go to the hash table Wikipedia page and look at collision resolution, you can see that there's a ton of different ways to solve collisions. The way that I showed you is called separate chaining, but there's different methods like open addressing and Robinhood hashing that you can read about if you're really interested in the topic. The point I wanted to make is that there is a bit of a downside. When we talk about fast lookups in hash tables, occasionally, depending on the hash function, it might take O(n). All right, let's keep going and expand our knowledge of hash tables in the next video.